Do you really know what's happening behind the scenes when a Flask app runs inside a container? In part 2 of this trilogy, we're going to show you how to turn each microservice into a fully functional Docker image, building, configuring, and running everything inside containers, just like it's done in real-world production. If you haven't seen part 1 yet, go back and watch it. We deployed the app manually, without any containers, to lay the foundation before moving into more advanced setups. Now let's get straight to it. Herbert is here and ready to show you how to get these containers up and running. Stick around because next week we wrap up the trilogy with part 3, fully automated deploy using Docker Compose. Let's do this.
We're back now in part 2 to deploy using containers with Docker. In other words, we're going to have the application running in containers. For this to be possible, you need to have the images available. In general, these images are stored in a repository, such as Docker Hub. We're going to create our own images because we're developing the structure of a system based on microservices. In this scenario, we have 2 main components plus the front end, which communicates with both. That's why we'll need custom images to meet the application's needs. These images will use a Python base image since the application was developed in that language, right? So what do we need to do now? We'll need to write clear instructions, descriptive code, to build these images. Now it's time to populate the Dockerfile files with the necessary steps. So let's open the Docker file for component 1 in our project workspace. I'll copy its contents here and walk you through each step. A Docker file is essentially a structured script where you define step by step exactly what you want Docker to do when building your container image. So what am I saying here? I'm instructing Docker to go to Docker Hub and download a specific version of the official Python base image for us to use in our container. Then I'm telling Docker to create a new directory called app inside the image. This directory will serve as the working space where the application files will be placed. The requirements file will be copied into this directory as part of the build process. Meaning I'm instructing Docker to copy the requirements file into the current working directory inside the image. Then it will execute pip install to install all the necessary dependencies. So all those steps we previously did manually will now be handled by the instructions inside the Docker file. When you run Docker run, all these steps are executed automatically as part of creating and running the containers. Further down in the Docker file for component 1, there's another task that copies the app file into the current working directory, which in this case is the app directory used by the container. Docker works in layers, and when building container images, copying files separately helps optimize the build process and cache usage. If you ever need to make a change to just this one file, Docker won't rebuild all the previous layers, only the ones from where the change occurred forward, because of its layer-based caching system that optimizes builds. No cache dir flag is used, so pip doesn't store a cache inside the image. However, Docker uses cached layers. If you change one layer, Docker won't redo previous ones, but will reuse them, saving time and resources. The expose command exposes a port in the container. Since our application runs on port 5001, we use this command to tell Docker which port should be accessible, ensuring everything works correctly. That's it, just these essential instructions in the Docker file. Now, let's add the instructions for the second component of our microservices project. The steps are basically the same. The main change will be the port, which for this component will now be port 5002. Likewise, we also have a Docker file specifically for our front-end component in this microservices setup, since we need to create a separate container for each part of the application. And here, in the same way, we specify only port 5000 for this service, always using the Python command to run the application inside the container. That done, we now move on to the step of creating the images based on this Docker build. Let's open a new terminal here. And in this terminal, we'll now need to access the specific folders in our project directory structure that contain our Docker build context, in particular, the Docker file, so we can properly run the Docker build command. Let's access our main project folder first and navigate to the component 1 directory of our microservices application. Once we're inside the component 1 folder, if we list the files, we'll see the Docker file that we just populated with all the necessary instructions for building our user service container image. That said, we can now run the Docker build command so that it creates the images. If we run the Docker image command, you'll see that we don't have any images created. The Docker build t command is used to add a tag to name the image created from this process. In our case, this image will be called TCB user service, making it easy to identify and use later. We can also use a colon when naming images to define specific versions, such as version 1 or version 2. This approach allows us to manage image versioning effectively, which is one of the main benefits of using tags in Docker. And this point here is to indicate to the docker build command that the Dockerfile file is located exactly inside this current directory of your project. With that specified, you run the command and it starts the build process, working in layers. It will then create the Docker image specifically for component 01 of our project, which is responsible for handling all user-related services within our microservices architecture. Now let's go up a level in our project structure and access the folder for component 2, which, just like the first one, already has its own Docker file. Next, we'll create the image for this component, which corresponds to the microservice responsible for managing the product part of our application. Similarly, we're now going to access the front-end folder where we also have a Docker file. This file is essential, practically mandatory, because it contains all the instructions needed to build the image. The Docker file acts as a blueprint, guiding the entire process of creating the front-end image. As the front-end has slightly more dependencies, the build process can take a little longer. However, this time difference is usually minimal and almost imperceptible in practice. Now, if we run the Docker images command, what we'll see is that we have the 3 images created. So we have the image of the front end, the image of the microservice responsible for the user part, and the image of the microservice that manages the product area within our simulation. The next step is to create and run the containers. But before that, let's address an important point. The communication between the components, between the containers. To ensure these containers can communicate efficiently and in isolation, we're going to create a specific network in Docker. This way, all the components will work within this exclusive network, allowing secure and organized communication between them. By default, Docker comes with 3 networks created. However, we're going to create a custom network using the docker network create command, entering the desired name. Once created, when you list the available networks, you'll see a new bridge network has been added. Let's move on to the next step, creating and running our application using containers. Now that we have the 3 images built for our microservices application, let's run 3 containers, 1 for each image. Next, I'll show you the command used and explain each part to you in detail. The docker run command is used to create and run a new container from a specified image. The D flag runs the container in detach mode in the background, leaving the terminal available for other commands. Without it, the container runs in the foreground and occupies the terminal. The container will be called user service in this setup, making it easier to identify and manage. Here I'm specifying the custom Docker network we've just created for our containers. This step is fundamental because many developers unfamiliar with Docker often have doubts about accessing a service running inside a container, since it is isolated by default from other services and the host. It is by exposing this port that access is possible. You define the external port you want to access, and then specify the internal port where the service is running inside the container. So, as we saw there, as we created our Docker files, each one has a port. So this component 1 works on port 5001. I'm putting the same port as before, but you could specify a different port if needed. And finally, I'll indicate which image I want to use to run this container. Now let's move on to our next container. We already have 1 container running, and I'm going to use this command here to create the second container. The only difference is in the name. Since I'm creating a new container with a different name, using the corresponding image, and mapping the appropriate port for this specific service within our microservices setup. And now let's go to our next container, which is our front-end service. For the front end, we're passing some additional information specifically related to environment variables needed for its configuration and communication with other microservices. Here I'm passing the environment variable, allowing the front end to communicate with the other 2 containers. This is essential so that the front end can display a summary and set up a dashboard with the status of all the microservices running. Now, by running the docker ps command, you can see all these running containers and check the status of each one. Here we have the name of the images, which were the images we created with the Docker file process running the docker build command. And here we have the names of the containers we ran for each microservice. That done, all that remains now is to test whether our application is actually running as expected. Remembering that it's currently stopped, let's hit F5 to refresh because we stopped at this part earlier when we did the traditional deploy. Hit F5 and there it is, your application, your microservice is running again, but this time it's running in a container. Now you have images with versions and several advantages for managing your application infrastructure. Instead of relying on a manual process of running multiple commands, you can use Docker files, which can be easily modified as needed for different application components. This approach makes deployment much easier and more practical compared to the traditional manual process. Before closing, let's stop these containers, because in part 3, to finish this fantastic Docker edition, we'll need to prepare and populate our Docker Compose file for orchestrating all our services together. The Docker Compose YAML file will be our next mission. So this docker stop command will stop the containers running in our project, and we also have a command that can remove everything, images, volumes, and containers. It forces them to stop and cleans everything up, ensuring a fresh environment. So this command, docker system prune, flag A for all, F for force, and volumes for it to remove all volumes. Why are we doing this here? This is important to ensure that no container is running, since the whole process will be done 100% automatically using a YAML file. This file will orchestrate all the container creation for us, and the execution will be done by Docker Compose. So if we go back to our application and try to access it now through the browser or API, it's natural that the services will no longer respond because the containers have been stopped. In part 3, we'll finish this edition of Docker by showing you how to deploy everything with efficient orchestration using Docker Compose. Of course, there are other orchestration tools such as Docker Swarm and Kubernetes. However, this is the first step in understanding the importance of Docker and how it works. Then you'll be ready to move on to the next level, using more advanced orchestration solutions such as Kubernetes. See you in part 3.
Alright, thank you so much for watching this video. And then if you enjoyed this content, please consider subscribing to our channel. Give us a thumbs up if you enjoyed this content, and then also please leave us a comment telling us what you think about this video and also the things that you'd like to see in a new video here on our channel, okay? And then if you're interested in mastering multi-cloud DevOps and AI with our help, please check the links in the description as well. Hope to see you in the next video. Take care and goodbye for now.